Okay, we can get started. Thanks everybody for joining today. I know people are still trickling in, it looks like, but we want to welcome everybody to join our webinar today. The Technical Issues Knowledge Committee is proud to present this webinar. So we can go to the next slide. And as part of the technical issues knowledge committee, we want to thank McNichols, annual friend of the knowledge community sponsor. And then we want to thank all of our current 1869 circle partners listed below, to thank the firms that support the AIA Chicago at the highest level. And with that, we wanted to and support the work of AIA knowledge communities and affinity groups. So I want to take a moment and just thank Scott and Toju, who will meet in a second, for presenting today. We'll have the benefit of working with their teams, and I think it's going to be a great presentation. So with that, I'll turn it over to them to get some more information.
All right. Thank you, David. Hi, I'm Toju Ashetago, and with me I have Scott Hamilton. And today we'll be discussing acoustics and the lead rating framework. First, a bit about us. Scott, would you like to introduce yourself?
Yeah, I'm Scott Hamilton. I'm our Central and South Region lead for acoustics, noise, and vibration at Stantec. Been with this group for about 3 years now, just over 3 years, and we're happy to be here. Looking forward to all the side chats that come from these types of topics.
All right. Thanks, Scott. I'm Toju Ashetago, and I've been with the Stantec organization for just about 2 years. Been in the industry since 2014. I lead our team's lead building enclosure commissioning program and manage several lead projects. Happy to be here. Thanks for having us. A bit about our agenda outline for today. First, we'll talk a little bit about our organization, Stantec, and kind of give you the Stantec overview, if you would, and our team, of course. And then Scott will talk about some basic acoustic principles, and then we'll relate that, those principles to lead, the specific lead credits or section, if you would, for acoustics, including recent developments in the lead rating framework. And the goal at the end of this is to summarize those principles, the relation to lead, and at the end have a question and answer session that will hopefully, continuing to more conversations. A bit about Stantec. So we are a global firm, 32,000 members strong. And as noted on this graph, we have offices all over. Our group is here in Chicago. So just for, placing, we are right across the street from Merchandise Mart. Nestled behind the glass towers there, at Wolf Point, and in the heart of the business district. We're looking forward, some of us are looking forward to just over a week from now with NeoCon and how that's going to change our commutes.
We're both CTA riders, so we're really looking forward to that.
Yeah. And well, some of our colleagues commute via the Metro. Again, we're not too far, just for placement. So we're here, we're local to many of you. And we do work all over the country. Scott, I know, collaborates extensively internationally as well. However, our team, as mentioned, is centered here in Chicago.
Yeah, I mean, so our acoustics team is about 130 members worldwide, and we're now on a 24-hour business cycle, which is very fun. I never get to sit on the couch and not have a message on my phone, but I'm refresh my memory. Do you know the total number for lead personnel?
Yeah, it's in the hundreds. I can share that. We do lean a lot kind of on our network, as project concerns come up. So it's in the hundreds. Here in Chicago, we're just about 15 people strong. We had a, kind of a quarterly meeting recently, so it was good to kind of just reconnect on the team level.
Yeah, so you have that personal touch, you have that local presence. You don't have to be on the phone with people crazy distances. We like being here in Chicago, and we intend to stay.
Yep.
Diving into today's presentation, we're going to get into the basic acoustic principles. And I often make the joke that it's an alphabet soup of acronyms that you often see when acousticians start talking about their discipline. Today's goal is to unbundle that alphabet soup and just highlight really basic principles so that you have that intuition for design. Not so much, we're not going to spend any time really doing any math really whatsoever. You'll see a few numbers, but they're not significant. So those of you that are not too keen on doing the math, don't worry. That's not what today's goal is. Today is just to talk about the basic principles, general trends, rules of thumb, and just give you that intuitive knowledge to make educated decisions. When we get into acoustics, we're really studying three different things that happen with sound in typically acoustics refers to enclosed spaces. We also incorporate that into the outdoors as well, but we're talking about the generation of noise, which if you're looking for another word to look at that, call that the loudness. We look at the transmission of sound between one space to another or one location to another. So we get into the concepts of sound reduction, attenuation, amplification of sound in some applications, as how sound reverberates through a space. And then finally, we get into the science of the reception of sound and how we hear and how we perceive sound. That turns into our audibility and clarity metrics. And so when we talk about sound, that's the three items that we as acousticians are talking about, and we're focused on those end results of those. What that typically turns into are three other factors that go in and play into those end results that go into the design side. And so we look at the background noise within a space. How does things contribute to that? How does sound behave within a space and its reverberation, and how does sound transfer between spaces in its acoustic isolation? And so let's break down and get into some of these acronyms. The first one you've probably seen a million times is a decibel or a dB. The fun little secret knowledge thing I love to share with people is a decibel is not a unit of measure. Is actually just an expression of a ratio. And so when you see the word dB, you need to see a few more letters. You need to see a little bit more to understand what they're talking about. Otherwise, we could just be talking about your cell phone reception because that's expressed in decibels. We could talk about your audio amplifier at home probably has a decibel meter on it. There's all these other applications of the decibel. When we apply to sound and acoustics particularly, we're often talking about sound pressure level. And that's because that's what our ears hear. We hear that fluctuation of air pressure in a dynamic way, and that's what our eardrum picks up, translates that into a signal in what our brain perceives. Now, you might also see sound power levels. You might see a whole litany of different metrics that come into sound that all get spat off of our fancy sound level meters that we wave around and operate on site. The important thing is you don't need to necessarily know all these things, but it is handy to have a cheat sheet like this that you'll come back to whenever you see this data going, wait, LEQ is different than an Lmax, right? Those things are different. One's an average, one's a maximum, one's a minimum, one's this day-night weighting. There's all these different types of decibels that get expressed. An acoustics consultant's job is to actually break that down, make it understandable for everybody. So if you're overwhelmed by this, you need to have that conversation with your acoustics consultant, making sure that they make it easy to understand. Some basic rules of thumb that typically exist when we talk about decibels is 1 decibel is what's considered a just perceivable or just noticeable difference. So the easiest way to, if you want to go home and play with this, you might have an older audio amplifier that has a decibel meter on it. You can sit there and turn that. And you can see, yeah, about 1 decibel is really all I notice. But what you'll notice is when you start cranking it up about 10 decibels, that's when your ears start saying, yeah, that's twice as loud. The average person will say that's about twice as loud. It's not. It's actually 10 times louder because of the way the logarithmic relationship of decibels works. But we're talking about feel, and that's where we need to communicate, and that's what we need to talk about. And so I made a little handy little table. This is all things that are in close proximity to you, by the way. Obviously, sound levels are different across a distance, and then we'll get into talking a little bit more about that. But what you can see here is that, you know, when you run your vacuum cleaner, you think that's twice as loud as your washing machine. If you're having a conversation, you're having a real hard time getting over that vacuum cleaner unless it's one of the new fancy ones, because it is significantly louder. It's 20 decibels louder on average. And so that's that ratio that you see, and that kind of helps you understand when people are saying, hey, it's going to be whisper quiet. Hey, we need to have an average conversational level. That's kind of the ranges that we'll look at and see. And I should have mentioned this before we started. We're going to have a link at the end of the presentation. This whole presentation is available for you to download at the end of it. And the whole goal of this is the reason I have all these tables is not to go through each item on it. They're to give you a reference to come back to later. So there's going to be cheat sheets throughout this. This is one of the first ones that I would say you'll probably come back to once in a while when we start talking about noise levels. The other sound rule of thumb that we want to talk about is that sound levels get quieter the further you get away from something. In a free field environment, meaning no walls, no reflections, anything like that, that turns into about 6 decibels per every doubling of distance you get away from something. So when you go from 10 feet to 20 feet, it gets 6 dB quieter. And this is another thing that you've probably observed out in nature and walking down the street. The other things you've probably observed in nature, though, are that when you have multiple hard surfaces all around, that sound reflects off that and gets it perceivably louder. So that's why things can sound can just travel down an alleyway, because you have that sound bouncing off both sides of it. The other fun one is you might not hear something until you're around that corner of the alleyway. And that's because if something's in the way, that sound path gets disrupted and attenuated. And so barriers, things like that can create these shadow zones. That's the term we use. It's much like the same way light projects from something and you put a barrier up in front of it and it blocks it. This can be modeled and predicted, and we do this constantly with our different tools. So in an urban environment, you can see, this was an experiment we did of just showing how noise propagates in a downtown environment. And of course, my old office, until a few months ago, we were in the Willis Tower. So I drafted the Willis Tower and tried to make it fancy looking. And you can see that phenomenon as these colors change. I hope you all can see my mouse while I'm pointing around, because I am a hands and pointing kind of person when I talk. But you'll see there's a more higher concentration of noise level right here. It builds up, and that's because everything's bouncing around and bouncing off of these hard surfaces and buildings. And as it translates around a corner and then around a corner again, you start seeing it kind of reaches that null level that happens. The same thing that happens here, you can start seeing as the distance goes up a building, you start to see the shadow zones. It's kind of fun because I think my office was like right here. So we didn't get that shadow zone, but you can start seeing the colors change as you go up the building, and as you get further away, you start seeing that dissipation of sound. And this is something that we're constantly working toward, is quiet environments in the urban setting, making sure we meet environmental noise regulations with a number of our clients. These are the tools, and that is the concept that we're constantly applying and looking at when we do these projects. Now, when we get into our 3 criterion, so background noise being the first one, you've probably experienced an NC rating being communicated to you either through an HVAC contractor or through another acoustics consultant. We have a number of these different ratings. You'll see NC, you'll see PNC, you'll see NCB, you'll see RC. All of them are single number representations of what we would call a balanced background noise spectrum. Typically means more bass. It means allowing for an environment where there's a conversation can be had. And more often than not, most people use NC in this industry. And that background noise that exists in space is everything that just happens in a space, generally steady state. And it's not human activity related. Typically, there's some one-offs for that, but that's what we talk about, is your HVAC system, your sound masking systems, your if you are next to an industrial facility or you are something like that, there would be some kind of compensation for that noise influence from an outdoor source. If your computers are running constantly, we work in data centers a lot, so that's a constant noise source that we have to deal with and manage. Any type of equipment, all those contribute to that background noise. And you see that throughout an entire building. There's all these different sources and all these other noise influences that can happen. Some of them are transient, some of them are steady state. It is important to note that often a lot of products are now marketed with an NC level to say, hey, it's quiet, and hey, this is going to meet your targets. Unfortunately, it's kind of a lie, and it's something you kind of need to watch out for. A lot of those NC box, or a lot of those VAV fan coil units, those kind of terminal unit boxes have an NC rating on them. And that NC rating is for an idealized situation, which usually doesn't exist in most modern projects. It assumes the box is not in the room. It has 20 feet of acoustically lined duct in between that source and the receiver. You have all these attenuation devices that are in there. And then in reality, our modern office design is exposed ceilings, exposed equipment, short duct runs. Often there's not acoustical lining in that, or even duct silencers or things like that knock down noise in ductwork that creates a higher noise level. And so those that don't trust NC ratings from a manufacturer, they need to be verified. And that's something we get into. This is actually a little bit of a preview into a space that we do these calculations for. And so you can see some return and supply ducting in there in the upper left. We have some acoustic lining in this project. You'll also notice it's a metric project. That's the one I pulled up. So these are not 500-inch ducts. But we see that a noise attenuation through the ductwork. We see how that turns into an effective NC level, and we look at that total contribution of everything together. And so using our proprietary tools that we have, this allows us to have a very smooth operation that we design spaces to meet that quiet background noise level that we're aiming for through all these different tools that we have available, like duct lining, attenuators, changing the HVAC design itself. This plays into the architectural design, because now to have a quiet background noise, we need to deal with a proper floor plan. Often we need to leave space for bigger ductwork because slow air is quiet air. And so when we speed up air too much, that causes other sources of noise within a ductwork system. Sometimes we need to have longer duct runs because we can't just cram everything in. We have to have some space to attenuate things, because sound levels go down as we get further and further away. That principle applies even in ductwork. And then also making sure we're locating equipment in strategic locations. We don't want a conference room with a bunch of air handlers above it. We want to have that in a space that's less noise sensitive. And then the last thing to talk about is often when we are at low NC ratings and things in the HVAC design and building background noise, it brings up that discussion. Do we do a plenum design or do we do a ducted design? And that plays into a lot of how we need to manage and look at that in the design of a building. The second concept we're going to talk about is acoustical isolation. This is easily defined as just simply the reduction of sound between one space or another that's created by barrier effects. Most often, we have our partitions. The common one you'll see is STC ratings. These are, again, single number representations of the acoustic isolation provided by anything. Higher the number, the more it blocks sound going from one space to another. It's important to also say that there is no such thing as soundproofing. There is sound reduction, and there are various degrees of sound reduction. There is no magic metamaterial that you put a panel on a wall and suddenly no sound goes through it. It's all about reducing some sound until it reaches a reasonable level that meets all our goals for a project. It's often one of the most disappointing things, I think, to a lot of our clients that we talk about is, yeah, there's no magic. There's no magic acoustic panel. There's simply SDC ratings and the various degrees, and frankly, the various costs that are associated with that. If you are experiencing this in the field, you might see a lot more of that alphabet soup, that SDC, that ASDC, FSDC, all of those. There's European standards, often because we're bringing products in from Europe and they follow an ISO standard versus an ASTM standard. So there's different testing laboratories. They generally all talk about the same thing. And it's important to also know that some of these are lab values, so they're tested in a laboratory under really strict conditions. Some of them are a field condition, and which means that's what we're experiencing in situ. And what we often see is in situ, we see about a 5-point difference between a lab value and a field value due to all the holes we poke in walls as we build a building, or just frankly, those different room sizes and ratios and scenarios that go from a lab to a field condition. When we get into what makes STC, at the end of the day, it's mass and separation. So we need more weight, means more blockage of sound between one space to another. And then as we get separation between those layers of mass, we get better performance. Those are the two tricks. It is nothing magical about it. And so if you look at all of our isolation products, all of the things that we do to build up a wall design, it really comes down to that. Let's add multiple layers of drywall because that's our most common commodity. Sometimes we get into other massive materials. So concrete's really common. We're seeing mass timber, not so much in Chicago, but in other markets a lot more. We get into other types of materials. We'll work into the design of a partition depending on the aesthetic need and the functional need of a building. And then we try to break those layers apart. So we'll put in resilient mounting conditions. We'll do two separated stud assemblies. When we get really crazy into acoustic design for like studios, theaters, and laboratory spaces, like high functioning laboratory spaces, we'll actually do this box within a box and separated entire structural designs. There's everything in between. And that all also then comes down to we need light tight construction. So we're also trying to seal everything up, everything that's coming in. We're trying to make sure that we don't have rigid connections across anything that is resilient. And so you'll see us dealing with like MEP penetrations of how do we bring in the ductwork and not compromise the wall. And then the last thing we'll get into is we get into flanking noise. Flanking noise is when sound gets into a structure, travels across it, and comes back out. That is typically not a very big concern until we get into really high STC ratings, typically about STC 60 and above. Doors and windows become the bane of our existence because we want to see through them. We want them to function, which means we're putting leaks in the system or we're putting low mass or even sometimes single layer items that are in there. And so how do we get better windows? Thicker glass, multiple layers of glass, separation between those layers. How do we get better doors? We seal up the perimeter of them with acoustical gasketing. We add mass to the door. We deal with the door lights, all of those kind of items that help build up a door's performance. And the last thing is HVAC often is another short circuit that can exist. And so when we deal with like transfer ducts between one space to another, it's too short of a duct, doesn't have any attenuation to it. That's a common noise path, and we call that crosstalk. Not going to go through this entirely, but when we want to talk about STC ratings, this is a place to start. These are roughly STC ratings of a number of partitions for CMU, glass, and drywall construction. Again, we're going to give you this presentation, so hopefully you have a nice little cheat sheet to come back to. Important things to know here, these are assuming mostly fully continuous walls. And the other fun one is this is assuming I want to say these are 26 gauge studs. I could be wrong there. But these are a thinner stud. So if you get a thicker stud in the system, a more like a structural bearing stud or things like that, you go to a wood stud construction, those number ratings all go down because we just stiffened up the wall and as we're tying those two partitions together. So these are rough rules of thumb to kind of help you mass out a building as you're trying to think about these ratings. An acoustician should review all these things or go back to your laboratory testing data from like USBGC, all those kind of other agencies that will provide that test data. The last concept we're going to talk about is reverberation, or essentially how sound persists within a space and how it echoes and decays and creates that quality. I think we've all noticed sound in different spaces. You enter a big open warehouse, you don't have a lot of strength to your sound. You have to raise your voice to talk, but there's this late echo that comes back. You get in a concert hall and sound just blooms and it's beautiful. You get in a room, if you ever have the unfortunate pleasure to be in an anechoic chamber, which is a test chamber where all the walls are absorptive, it's kind of maddening because it doesn't sound right and it feels weird. All that changes how we feel in a space. And that is from, typically we express that with our reverberation time, which is literally a measurement of how long it takes sound to decay in a space. It's quantifiable, it's quickly measurable. And so there's some trends that come into that. The bigger the volume of a space, the higher the reverberation time. And that's just because sound is bouncing around and bouncing around and bouncing around. And then the other part is acoustical absorption. So we have reflective surfaces and we have absorptive surfaces. And we'll get a little more into that in the next slide. But the more absorption that's in a space, the sound gets transferred into heat energy and dissipated because energy has to be transferred. All that energy has to go somewhere. When we have higher reverberation, means lower clarity. When we have higher reverberation, also means generally the loudness in the room goes up. The best analogy I have for that is we all probably as kids played outside, came inside, and one of our parents told us we need to use our indoor voice because we were so used to adding all this extra effort to talk outdoors to cover a longer distance and not having all those reflections building up the apparent loudness within a space. We come inside, now we're way too loud. And suddenly we're talking at such a high effort because we're used to it. That's because partly the room loudness is adding to that apparent noise level or sound level in this case. I talked about acoustic absorption just a second ago. Acoustic absorption is literally, does the panel reflect sound or does it absorb it and dissipate it? We express that with an NRC rating. I hope this is the last. No, it's not. Sorry, I thought this was going to be my last acronym. It's not. The NRC rating goes from 0 to 1, 0 being perfectly reflective, 1 being perfectly absorptive. You will see some products claim higher than a 1. That is scientifically impossible. They did their testing wrong. If we look at absorption within a space, it is basically a function of that NRC rating times the surface area of coverage in a space. So if we have a room that is 100% covered with an NRC 0.5 material, we have that effective rating. It is directly equivalent to half the room being covered by an NRC 1 type of product. That lets us exchange things, mess with our reverberation time, play with materials, things like that. You'll typically see acoustical ceiling tiles in most spaces offer a great rating, usually between 0.65 and up to like 0.9, depending on the material. You'll see carpeting is often misconstrued as an acoustically absorptive material, probably because we all moved into an empty apartment and rolled out the rug and suddenly the room calmed down. Generally, carpet tile on concrete is like an NRC 0.2, not very absorptive, has some properties, it's better than bare drywall. And then the last one you'll see a lot of is acoustic foam. And frankly, that's everyone's image is acoustic foam, that triangle stuff. We often try to avoid it just because I think we've all seen when the bad foams get installed or the fireproofings wear off on that, they tend to be an unsafe material. So we work with acoustic materials that give us that acoustic performance, gives us that high absorption, but also tend to play better into fire ratings, gets better into high wear and tear. If it's a high touch environment, can it handle abuse resistance, all those kind of things that factor in. All right, when we get into clarity, so again, this is the end result that I've been trying to get to. This is how I perceive sound in a space. And so in a highly reverberant area, the clarity goes down. It gets harder to hear, not because it's too loud or too quiet, but because there's too much echo within a space. And what that is the ratio of early energy to late energy. So when we're in a room, we're hearing things, sound is arriving to us all the time over a period of, it could be anywhere from like 1 second to 2 seconds. Sometimes that an event happens in a room. Our ears have this amazing ability to kind of break that down into windows. And usually that first couple milliseconds of sound that arrive at us, we can perceive as what we call direct sound or what we can hear. And then there's all the reverberance that we interpret as that room's bloom or that echo, or sometimes when that late energy gets too overwhelming and it comes up, that means we're no longer able to hear well. Unfortunately, there's like 4 or 5 different metrics that tend to exist within a lot of these criterion that you see, particularly the FGI guidelines for healthcare will list all 4 of these. And they're different rating systems. So it's either D50, C50, articulation index, speech transmission index. There are all these different kind of metrics to explain it. But what we're really trying to say is understandable, not understandable, clear speech, not clear speech. And we can see that. I hope all of you have good headphones on because I've made some audio examples. So when we talk about dry speech or no real late energy, it's only direct sound. Oh, I went too far. You'll hear a sound like this. When it plays, there you go. But as we add reverberation, it gets a little harder. And that's getting to that level where it's just incomprehensible. And that's because there's too much late energy versus just that early energy. So I hope that kind of demonstrates that and kind of gives you some feel for it. The last concept is privacy. Again, as I was saying, we're trying to get to these end results. We can talk about SDC ratings. We can talk about background sound. We can talk about reverberation time. But at the end of the day, it's about that experience. And privacy is that really that end all be all of, can I hear something between another room? And again, you'll see a number of acronyms come into here. Actually, funnily enough, you'll see articulation index come back because the opposite of clarity is privacy. And you'll see STI come back on this table too. But what we like to talk about often is speech privacy class, because I like to communicate with clients just on an anecdotal level, not experience any of these numbers and not overwhelm everybody with everything that I just spent the last 30 minutes talking about. And so what we get into is, do you want a minimal, a standard? Do you want speech security? Do you want high speech security? Do you want absolutely confidential? And we work with our clients now, and often this is best often when we actually talk with the end client to help them understand this is the expectation right off the bat. And that's where we want to have a good just back and forth where we value engineer the project before we have to value engineer the project. So we're designing a space that meets the client's needs and expectation right off the bat. And what that comes down to most often than not is privacy. And then what we talk about when we talk about privacy, it's really it's all three of those variables that we talked about before coming into play. So we talk about the loudness of a source, we talk about the reduction of sound between two spaces, and we talk about the background noise level within that space. And what it is it's a play between all these. So if we assume a scenario where we have a fixed noise source, let's say that variable doesn't move, but we can adjust the wall and we can adjust the background sound that comes into the scenario. So we have an average person talking once it loads. So as we add a wall to the system, it will get quieter and quieter. And so you reach a level of imperception or incomprehensibility of it. Now, if I can't build up the wall significantly, I can do something else in like an open office environment. So we start here again. I don't know why this one takes so long. I'm sorry. We can start adding extra background noise in. And we can get to pretty extreme levels. And that helps also create that masking and creates that scenario. And so we need to pick our background noise levels appropriate for our environment. We need to pick our wall types appropriate for our environment. And that's where we have to make that decision based on privacy and quantitate it instead of just saying a one size fits all with STC ratings when we design a space. The last thing we get into is that acoustic clarity and how we model that as well. These are just some photos or videos of some of the tools we use to both visualize and also help people experience what we're designing in a space. So on the right, you can see a very generic auditorium and how sound is reflecting and also arriving to locations at different times, especially those first 2, 3, 4 reflections off of a building. And we try to provide finishes at the right spot, manage those early reflections, because like, oh, what just happened when a late reflection comes to the stage, it's bad. At the right time, it's great for a musician or a speaker to hear something, but if it comes back too late, it's a slapback echo and it can actually throw the musician off beat. The other side is on the right here is just one of our acoustic simulators running. We have a dynamic head tracking algorithm that we use to help play back items, and that's because we have 2 ears, and if you look at people in a space, we're constantly moving. And that's because we're constantly recalibrating our hearing in a space. Even if you don't realize it, you're doing it because you have educated ears. And so what we like to present these kind of informations, the same audio demonstrations that I was doing here. Now imagine an environment where you have a 3-dimensional, I can turn my head, now I can hear that back wall, and I can hear this, and I can hear this. And so these are the tools we love to use because I think we can often make a lot of these recommendations and avoid, or we make them using a chart, or we make odd kind of recommendations and people have no attachment and no feel for it. This allows people to actually hear, feel, experience spaces before they commit, and helps us design spaces better because you often find that middle ground faster when you do that instead of the extreme designs.
All right.
I'm going to take a break from talking and hand it back over to Toju.
Thanks, Scott. Definitely appreciate that overview, refresher of concepts, regarding acoustic design. Now, for this part, we will be given an overview of essentially how that translates to lead credits and lead credit documentation. And as many of you might know, LEED version 5 is here. You can register for a LEED version 5 project. And just a bit of an overview of what the intent is. Some of the language noted moving beyond neutral or sufficient spaces toward human-centered design that supports customization, enjoyment, and emotional connections. Lead language. At the bottom line, I think from how that's defined is, how do you feel when you're in that space? And something that's come up in some of our discussions, even before, LEED v5 was ratified, is that very often from the acoustic design side, LEED certification is not necessarily driving those considerations. Privacy is one. There are other considerations as well. Something that's interesting is, at least from how it's laid out right now, holistically, it looks to be more in line with what you would call, or what would be kind of the optimal design process from an acoustic perspective. So LEED v5 focuses on an integrated approach. So previously, the categories that had to do with background sound, sound isolation, and reverberation, they're now combined. And the idea is to look at rooms, categorized by acoustic sensitivity. So, and there's an inventory at the end for the percentage of rooms. Won't go into those details right now, but it's more of a holistic approach. Something to note is LEED version 5 is not prescriptive. It does not prescribe the acoustic criteria. Basically, it gives the acoustical consultant the latitude to develop their project-specific criteria. And if you choose to go for LEED certification, you will essentially explain that, narrate that, defend that to the LEED reviewers, which very often, aligns with what we've seen on some of our projects as well. We'll talk a little bit more about this, but there were separate requirements for schools versus healthcare. Now that's kind of taken away, as you can see here. One interesting aspect is that basically those prerequisites, for example, schools had a prerequisite, healthcare did not, and had two different points. Essentially, all of that is taken away, and you're given pretty much two pathways for moving forward on the LEED v5. The path one is you're expected to map out your acoustical expectations for indoor and outdoor spaces. And path two, you map out the acoustic criteria and what the expectations are as well. Something I should note is overall, the acoustic documentation for LEED performance harks to more specifically, one of the impact criteria for LEED, quality of life. So LEED v5 overall has 3 impact criteria: decarb, quality of life, and ecological conservation and restoration. Basically, the ethos of this is, how does this acoustic design affect the quality of life of the occupants? And we do have, like Scott mentioned earlier, there will be, this presentation will be available to you, and there'll be links to resources that are related to these credits.
Yeah, there's a number of changes that are going to come. For me personally, I think it's a little bit more of the same. and I'm looking forward to it. I've had the pleasure of, while not being on the lead committee, being friends with a number of them and kind of influencing a little bit of how this is going. So the prescriptive design elements I might be partially responsible for accidentally. What when we used to have to pursue lead accreditation, or we didn't know if we'd propose on a project with lead accreditation, used to be an interesting dynamic. So we'd always add it as like an ad services. There's a filing fee. We have to create all this extra documentation, package it. Lead V4 had a very complex spreadsheet we had to fill out that didn't really align with any of our products. So we actually retooled our products to fill them out. And so a lot of our products have been building towards that objective requirement, while at the same time, when we have our design, we're talking about that prescriptive or objective requirements. So with that, as we move forward, we're looking forward to one, I think a lot of our existing deliverables that we try to educate the client with become submission documents.
Right.
So I'm hoping we can actually kind of integrate how we approach our lead submissions moving forward, that we're not creating separate reports. We're not going to have an extra fee. And then the other fun one with that was always we'd have that as an add-on fee, because we never wanted to let our base fee come up too high, or we wanted to be competitive when we're bidding on a project. But what always happens is, like, we get halfway through the design and we decide we're going to pull the plug on something like the acoustics design, or they're going to do something, and I have to sit there and cross my arms and say, well, we're not going to meet lead certification anymore. And that's the only thing that keeps that in the project, or that's how we kind of work through that solution. Now, theoretically, we don't have that same, like, here's your line in the sand.
Right.
And as well, it doesn't have that weird project dynamic where we just go, cut it off, we're done.
Yeah. And it aligns with some real world experience we've had on projects, for example. So, let's say you're looking at a healthcare project with an addition. So you have a historical lead submission, say 2009, right? And you have a lead V4 project coming up with the, specific criteria. And you have an acoustic consultant who's, picking up that design conversation, essentially. And some of you might be familiar with the credit interpretation request, right? Very recently, we were involved with one that basically wrote to the GBCI and said, here's our methodology for using, and correct me if I'm wrong, but again, acronym soup, speech privacy potential in lieu of speech privacy class.
Yeah.
Right. And so instead of resorting to these one-off procedural processes, we, in theory, with lead version 5, have a more kind of unified approach moving forward. Now, today, what does it change? We guess that for a lot of projects that are already registered, you'll be continuing with more of the same. However, with the rating, with the lead V5 certification process being open, we see more project teams kind of being open to porting to the other to the newer framework.
Yeah, I think another important thing to note is that the acoustic requirements probably aren't changing that much. LEED itself never actually prescribed any new rating system or design standards. What they did was they deferred to other professional standards. So there's ANSI standards for schools. There was the FGI sound and vibration guidelines for healthcare. There's local municipality rules for environmental noise. All those kind of things play into them just saying, here are the professional standards, meet those, and you get the LEED credit. Not, here are new requirements or recommended construction methodologies. So I think all those standards are basically going to be those standards. They're not going away. And frankly, that's still going to be what I back up against or reference when I start a lot of these recommendations. We sit on a number of these panels, we contribute to them. These are good benchmarking standards. Now there's scenarios now where we can still pursue LEED with variances from the standard based on different adjacencies, based on over design, under design in certain scenarios. So a fun one would be partitions in offices. We love glass right now. It's in vogue. We love it. We want to use single pane glass. That is probably STC 30 to STC 35 construction. we need a privacy rating that is more akin to STC 50 to meet those requirements. And if we sit there and we only look at STC ratings or partitions, you don't meet. But if we start saying, yeah, we're going to have a sound masking system, we're going to deal with this, we're going to create privacy through all those other metrics that add up into that environment. Now it's justifiable to deviate from that standard, and any lead reviewer should be agreeing to that. Now, we might experience a few hardliners in the review process, but we're going to cross that bridge when we get to it. So to kind of give some idea of that, that's the new flexibility. It creates complication, but I also think it provides a better approach moving forward to holistic design. Let's talk about timeline.
Yeah. So this is an overview of the timeline. We're currently, past project or the project registration being available. And, as mentioned, we expect currently more of the same. Certifications typically come a little later after that. And one question we've gotten is, or when is Lead V4 being sunset, right? We're expecting that sometime at the end of Q1 for 2026. And then what happens? The practice, it looks like from guidance from the USGBC, isn't changing in that, and by that I mean for Lead V4 and Lead V4.1, you can continue certification until it's officially sunset. So 6 years after you register. So is there a world in which we see a slew of projects being registered for V4 and V4.1? Well, that would align with what we've seen before in the past. However, for the specific topic of today, acoustics, and the practice that's, we've established as common, we do see the possibility of project teams taking advantage of the opportunity to switch over to Lead version 5. And something we noted on the last slide for the exams, basically the material is going to take some time to work its way into the exam process.
Yeah. We have a number of slides remaining. We're not going to cover any of them today. They are in the presentation, and they are meant to not be something that we go through. They are meant to be a cheat sheet for you moving forward. So as Toji mentioned, Lead 4 is not going away. And as I said, these professional standards are not going away. So we amalgamated all of them into a nice little package here based on the old 4.4 or 4 and 4.1 frameworks. They will still be the basis of design probably for Lead 5 projects moving forward, because as I said, FGI guidelines, ANSI guidelines, all those kind of building construction guidelines, not going away. They're still going to be there. It's still going to be good design. And so you'll see throughout here all the different types of HVAC, sound transmission, reverberation time, sound reinforcement, and masking, all the concepts we've been talking about before and how that plays in. There's STC ratings based on adjacency combinations. There's reverberation time considerations based on the use of the space. There's background noise recommendations based on those spaces. And you now know how to read all of these things, even possibly the sound masking and sound reinforcement requirements. You kind of know what they're talking about now through what we've gone through with this high level item. As we mentioned, the school prerequisite is going away, which means you don't need to meet this now to have a lead rating. I will say schools, background noise levels, exterior noise concerns, and reverberation time, very important things in schools, especially as we are designing spaces more and more for neurodivergence and special needs considerations. That's a really important thing that we go above and beyond the average poorly designed classroom of the 1960s and step into the future and provide a better learning space. So you have the prerequisite covered, and then you also have the actual coverage of additional requirements for that additional lead point. That's all there. It's a very long table and it's very complicated, but those ANSI requirements aren't going away, or the guidelines aren't going away. Healthcare previously had 2 points where they actually divided the topics up between them. As we mentioned, there's no longer there's no longer consolidation, or sorry, there's no longer separation. Now it's acoustic design is acoustic design. You get that point for going for it, and then or for laying out your goals, and then you get that point for showing compliance. So it's we have 2 points available. But it's a different approach, and now you have to think holistically. You don't get to say we had a project recently where I wasn't the acoustics consultant,
Yes.
but you are the lead consultant on it. And for those that don't know, Toju and I often sit next to each other, so we're always chatting. And you were asking me about that, and I was like, well, if you don't meet this requirement, you can only get one of these points.
Right.
And so that kind of stuck the project, whereas I think it was acoustic finishes was where you were stuck on. And it was a clean room environment. So perforated materials don't work in a clean room environment. So there's a reason to go for a variance on that space, especially if there's not acoustical considerations or communication happening in that space. So under lead V5, that space actually might be a more approachable solution.
Yes. That's a great point.
And so healthcare's got a lot of them. The last one, there was a pilot credit for data centers for making them quiet. And so we mapped that out. I actually don't think I've had a project where we've been able to go to it, because this is actually more stringent than a lot of the background noise criterion that are out there. And while I believe in quiet spaces, sometimes we have to manage the budget of a project. And so wrapping up, we've gone through all these different acoustic terminology. I hope everyone's comfortable now and you have some language to communicate over acoustics. So when I start saying it's a live space, it's a dead space, it's a loud space, it's a quiet space, you have more of an understanding of what we're talking about, and you can work with your teams better. And you also sort of know already, all right, we need high privacy. That means we need good walls. That we need clear communication space. That means we need acoustic finishes. You have some of those building blocks to know where the strategy is going, and then you can get into the specifics once you either engage a consultant or just go off best practices in different scenarios, or maybe you have a template design that you're working off of. You understand where those pieces are. The other part we talked through was the lead transition from V4 to V5. Hopefully you now have that cheat sheet as well of that wonderful timeline, so you know when to jump on lead 4 and when maybe we should have a strategy talk, and maybe we should go for V5. Maybe we want both acoustics points, so now we can go for it. And how all those methodology changes and where that's going to affect you. So a lot of content. Thank you all for sticking with us. This is a QR code. This will take you to a Google Drive folder, which will have both our audio examples available for you if you want to play around in that background noise versus isolation, get a little more experience, play around with that. That's there and available to you, as well as a PDF copy of this entire presentation. And if you want to share this with your teams, by all means. If you want us to come in and chat with your teams, we're available. Give us a call. This is our contact information as well. We're happy to chat with you about both these items. And thank you for having us. This was great.
Thanks for spending your lunch hour with us.
Yeah. We have 2 questions that are in the chat right now. The first one being opinion on acoustical structural glazed concrete masonry units / tiles with perforated surface types. So that's an interesting dynamic because you have some things going on. So if you talk about like a glazed CMU, that means you've got a product over top of it that takes a lot of the frit away from it, and it makes it really smooth. So that actual face becomes an acoustically reflective surface. More so than unsealed CMU has a little bit of acoustic absorption to it. But when you get into perforating CMU units, and so when you see acoustical block thrown out there, usually there's a slot for that hollow core in a CMU unit. Sometimes they'll stuff fiber in them. Sometimes they'll just leave them open. That will have some resonance and acoustical absorption products in there. Acoustical CMU is an interesting thing. It's great for high abuse areas where you need protection, so gymnasiums, things like that. They're challenging because you always want to keep them out of reach of people, because people love to stick time capsules in them for later, or gum wrappers or whatever, particularly in schools. And then they're challenging for outdoor environments because you have all the entrapment concerns. You have birds sometimes can nest in them if the perforation's too big, all those kind of fun things. So there are interesting products. There's a lot of scenarios where they work really well. Particularly, again, that high abuse area, gymnasiums, places like that. But Other times a better product exists. And then you also lose some of the benefit of CMU, which is you have a big, massive weight of wall. And so often when we're talking CMU, we're talking grout filled CMU. So we're getting a lot of mass up there. And that's because we're trying to block sound from one space to another, particularly in gymnasiums. There's a lot of activity. So if we are doing perforated CMU or an acoustic CMU, often it means there's a wall on the other side to beef back up that wall and get that acoustic isolation. So that's a challenge. But there's applications that make sense. It's all about finding the right product for the right application to get that absorption in the space. Because honestly, for me, often the type of absorption doesn't matter so much. It's about getting the performance and meeting the aesthetic need and the functional need of a space. We have one other question. Comment on integration with OSHA requirements, regulations for workplace. So OSHA does have a number of recommendations regarding sound in workplaces. The most common one being sound exposure, meaning how much noise are people exposed to throughout the day, factory environments, construction, those types of activities. And then that breaks down into the levels of sound. So there's you could spend your whole day having 50 decibels. You could have your whole day being exposed to 90 decibels, particularly if you're running a jackhammer or something like that. So it's the level of sound as well as the duration of it. Both factor in. And so OSHA allows higher sound level exposure if it's for a short duration. If it's a full 8-hour day or even longer, those levels come down, 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 down. I think it's actually a fun anecdote to talk about that OSHA regulations should apply to more things because most of us are getting an overexposure of noise every day by means of our AirPods. Especially if you're listening to headphones blasting music for 8 hours a day, chances are you're experiencing more noise than a construction worker because construction workers will wear your protection to get their levels down. The other side of it is loud office environments, those kind of loud places. It makes it harder to hear, makes it harder to be safe and communicate with each other, as well as you get worn down in an environment. It's harder to concentrate. There's paper after paper about the open office being harder to concentrate in. So we need to manage those noise levels in workplace environments too.
For sure. And one anecdote I shared with Scott, kind of talking through this, was my first job out of college. I worked alongside another acoustical consultant whose job it was to sample noise on patient wards here in Chicago at a major hospital, tertiary level hospital. And we saw, high sound levels, even in the middle of the night, just experienced by patients on the general medicine ward. Pretty interesting.
Yeah, those carts add up really quickly, especially a bad wheel on a cart. That becomes a problem. Yeah, we've done some projects where we do 24-hour monitoring of that, and you'd be amazed how much of that's there. All right, well, we're at the end of our questions here in the queue. I'm happy to stick around for a little bit longer if any come up or if anyone has to have a little bit of a discussion. But thank you all for joining us, and hope you all enjoy the rest of your day here with acoustics in mind as we keep working.
Thank you.
Thank you all. Our attendee list is dwindling, so I think we can close down.
Sign off. All
All right,
righty.
thank you all.